Hi, in this section we are going to talk about Plackett-Luce trees. We are going to use two examples, the sweet potato and the bread wheat data. So let's start with our R project. Let me put it over here. And then this is the folder of our R project. You can also see the slides and all the outputs of this section here in the topic number 8, Plackett-Luce trees. And then we have all that we are going to do in this script in this section. The packages that we need are Plackett-Luce, KivuCalc, GoSet, Patchwork, ggparty, the package ClimaTrends, NASA Power, and ClimOptools. So this is our project that we are using since the beginning of this course, and I'm going to open it. Just a moment. I can even put it a bit bigger. Let me put it a bit bigger so then we can see it better. So it's tools, global options, then appearance. So then we can put it just a bit bigger so we can see it better. Now it's better. So then, as I was saying before, the package that we use is the Plackett-Luce, KivuCalc, GoSet, Patchwork, ggparty, ClimaTrends, NASA Power, and ClimOptools. So we call each of these packages using library, and it should be installed in your computer, in your R library before. No? So if you don't have any of these packages, just use the function install.packages, and then you can install them. So then I run this, and that's the same thing that we did in the previous section. I will read the sweet potato data. So the sweet potato data is in the folder called data, and then I use data / sweet underscore potato .csv, which is the name of the file. If I check it here, list files data, and then I can see the name of the file here, sweet potato /csv underscore potato .csv. So I will open it and I will call it, the object will be called dt. So I open it with the function read.csv. I will do it again just for you to see. dt, arrow to the left, read csv, so then data, sweet potato, and remember to always put the extension of the file. And here, as you see, as I was explaining in the previous section, this data covers two trials in Uganda and in Ghana. And for this exercise, we are going to use only the Ghana data. So to do it, we filter it, and to make the filter, we can even make it a bit better, like we can create a filter called the keep, for example. And then, for example, every DT country, I want equal, I want only the data that comes from Ghana. So if I put a DT country, for example, if I type it here, I will get the vector with the names of the countries. Now it should be Ghana or Uganda. For example, if I do table this, and then it shows to me that I have 1015 points from Ghana and 418 for Uganda. So I want only the Ghana data, so I will create this vector called keep, And then with this vector keep, this is a true-false vector. So that everything that is true means that the data comes from Ghana, and everything that's false means that it comes from Uganda. And if I do table with this one as well, table keep, this will result the same thing as we saw before. No, false, which is Ghana, so it's for 480, and true, which is Ghana, 1015. So what I do now is apply this filter to the data. No? So dt, it will still be called dt, and then dt, and then I want to apply it to the rows. So I will put keep here, and then I want all the columns. So keep, comma, and then I leave it empty so R knows that I'm just filtering the rows with this vector keep. So then with this, I have 1015 entries for Ghana. And then if I do head here, I can see the data set here. And then there's a country, district, gender, trial, which item A, B, and C, and which one was the best and worst. In this case, they only evaluated best and worst overall. So then the first thing that we are going to do is fit a simple Plackett-Luce model without any covariate, just to see how this works. To do this, we need to convert the data into a Plackett-Luce rankings. So here I use the same function, rank tricot. So I put in the input data, I put dt, and in the items is the name of the item, now A, B, and C. And the input is the name best and worst overall. So should follow this order, the best first and the worst second. And then I have my ranking called R. And if I just click, for example, head R, I can see here the first rows of this. And why these numbers? Now, why I have this if instead of having 1, 2, 3, why I have this? Because I applied the filter and then it keeps the index for the rows that comes out of it. So if I look at here also dt, I see 419, which means that it started from this, the data from Ghana started from this index. But this is not a big issue if we take care of it. And then to fit a Plackett-Luce model, we use this function called the Plackett-Luce. So let me just take a look at it. And the Plackett-Luce models this is the documentation for it, and it shows set that fit a Plackett-Luce model to a set of rankings. The rankings may be partial, which is our case, and include ties or arbitrary order. So the ties mean when there is no actually a decision regarding the which one is the better or worse. But our case is the ranking incomplete partial rankings. And this is all the arguments that comes. Then there is explanation for each of them. But we are going to keep it simple, and I will just use the first argument, which is providing the rankings. And then I will call it mode. So let me do it again. Mode Plackett-Luce, and then R, this object called R here, my ranking. And then if I just do it, and then that is it. And with the function summary, I can take out the summaries of this node, say like the coefficients and all the estimates of this model. So if I do summary mode, I can take the summary of this. And then I see, for example, that the first element is set as the reference. They are arbitrarily set as 0. So then everything is compared to this element. So then I see the p-value, so the significance compared to the reference, which one if is better and worse. But if we look at here, this is not so informative. So sometimes it's better if we set up the reference based on what we are looking for. So in this case, for example, I understand that from my colleagues that implemented this trial, that the reference of this trial, no, the variety that is like the one that we want to compare if the variety is better or worse than the one that we are trying to implement, is this one called the Sari Neomingre Obari. So this is like the reference for all the traits. No? So then we want to see whether the other varieties are better or worse than this one. So to do it, we just need to, I will create one vector, one element called the ref with the name for the variety. And it should be the same name. So if to be sure that you are using like the same structure of the name and you don't have anything different, because since R is very strict to the strings, you need to put the exact names for it. So one way to do it is that you just need to look, for example, in you can take out of the summary, so maybe we can do it just copy it here and paste here. Or you can also take for example, from the item names. So for example, if you can just, for example, unique dt item A, and then I see here the name, so this one, and then I will copy and paste it here. So then I'm sure that I'm using the right name. So then reference, and then if I do the same thing, summary, but use the argument ref for reference, so summary, and then mode, comma, ref equal ref, which is this one. And then now the variety Sari Obari is set as 0, no, by default. And then we can see if whether the other ones are better or worse than this one. So for example, we see that the estimates here are basically all negatives besides this one. So the only genotype that it seems to be better than Sari Obari is this one called PG. Let me see. PG17 136 N1. So this it seems to be the better because the coefficient is higher than 0, no, than the 0 that was set by default here. So then everything that's higher than the 0 or positive, it's better than the reference, and everything that's low or negative than that, it's worse or have lower lower likelihood to be the best one. So, and then we have this one. So this is it. And then also there is one way to see these, these coefficients in a plot. To do it, we can use the function from the package QV calc. And then let me see, we do like this, a QV calc, and then we put the name of the object, which is the mode, and then we set the reference as well. So then this will return to us the estimates and the Kasi variance error, and from which we can take the error bars also, no? From this model. And also QVCalc has a plotting method for it. So then we just need to put plot, let's say KV, we'll save it as KV, for example. And if I do a plot KV, it will return to me this kind of plot here with the name of the varieties and the error bars. Okay, and then the reference is also set to 0, so it's this one, no? This one, the last one is 0. I will show to you also how can you save it. And then another thing that we can also do here is take out the coefficients, no, the log worth or the worth parameter as probability of winning. So the first thing is, for example, when we do the function called coef, and then we put the mode, for example, and then the reference, we get the coefficients from the model, which is the same thing like this, no, the estimates. but these are in the log format. No, they don't inform you so much if you don't have the reference, or you just need to look at it. No, so it's not so informative when you want to compare with on something else, or some more like a probability of winning. So to get the probability of winning, what we do is that we use the same function coef and then mode, and then we use this argument called log false. So we don't want the logarithms, we want actually the probability of winning. And this will return a set of different values. And the sum of these values should be always be 1, because this is the probability of winning. So the sum of it will be 1, because then it will be 100%. And each of the varieties will get a portion of this probability. So then we know which one has the higher probability. I will save it like coefs, for example. I will save like my coefs. And then if I do sum my coefs, the sum should be 1. And I can also see the order, which are the order of the best genotypes based on the probability of winning, with this function called sort. So then my coefs, and then it will give to me the order, like the probability of winning for each of the genotypes, and then the order it's from the lower to the higher. So if I want to know, for example, this one PG 17 140 and 2 is the genotype that has the lower probability of winning. So it's the weakest one. It's the most less evaluated one, like the less appreciated one. And if I look at the other side, so this is the PG 17 136 and 1. So this one has a 11% of chance to win against the others. So this is the probability of winning, also 111. So it means that it has a 11% of chance to win against all the other elements in this, all the other varieties in this set. So this is what the probability of winning means here. And then we can also, as I showed before, you can see in the order. So then you can identify the order of the elements here. And if you want to save it, to keep it in your computer for further analysis, or if you want to show it to someone else, remember we already have the folder called here. The folder here is the output. So to save the summaries as a text file, what we do is that we use the function called capture dot output, and then I will use a summary mode. This is what I want to capture. Now this is the output that I want to capture, is the summary of mode. And then I will put the name of the file, which will be output on the slash summary mode sweet potato .txt. So I want to save it as a text file. And if I just run it, so then this is already here. It's a text file with the same output. So this is a text file that we got from R with the summaries. And I can do it for any other thing that I want to capture as a text file. I can even put more things here. For example, if I want to put the same thing, and then I want to put the coefficients, for example, I just need to add it, and then if I run it again, the coefficients will be here as well by the end, you see? So these are the coefficients. And I can also put like something like this. We can also put something like this. For example, cat, which is to put a title. So model coefficients. So then it is no, it's print. If I use print model coefficients, and then this will be there. No, well, something wrong is happening, but it's okay. Just with this, it's okay. So then it's how we save now with capture outputs. I just need to do it here, and then it's there. And then to save the plot, now this one that I was the QView calc plots, the same thing, now PNG, and then I want the file name will be output QV calc mode sweet potato. Let's call it like this. .png, and then I will put the how is the dimensions of the plot. Now, so let's say that I want width of so it should be bigger, so then it can capture the name of the file. So let's say 30 centimeters, and the height will be 15 centimeters. The unit will be centimeters, and the resolution, let's say 400 dpi. So this is it, and then I will put plot my key view, and then dive off to close the device, and then let me see here, something is wrong with this plot key view. Plot key view. Yes, I need to put a T here, so output. Yeah, so this happens. So output underscore slash KiviCalc mode. So then if I run it, then I can see the plot here. So here's the plot. Okay. So here's the plot with the varieties in the y and the x axis, and then the estimates in the y-axis. And now there are another option in Plackett-Luce that we can also add covariates, so we can see if there is any influence of a special covariate that talks about how is the rankings, how any covariate can drive the rankings in the Plackett-Luce. And to do it, what Plackett-Luce does is that it takes the approach of the recursive partitioning trees. So as you saw in the video from Heather, so they take it and then they run the model with without covariates, and then it starts to add covariates looking for instabilities in the model, in the data. And if they find an instability in the data, so then this means that there is an influence of the covariate in the ranking. So then it splits the tree, and it go doing this until there is no more instability to find. And if you want more details, also I provide the link for the paper, for Heather paper, which shows how this is done, and how all the the background of this and of the Plackett-Luce and everything. The paper is it's open access, so it's just need to click on this link here. And then I will add two covariates. I will add the covariate age and gender. So this is like to bring to you a perspective that we can also use socioeconomic variables to check how is the influence of the rankings based on the evaluators characteristics. So I will use the age and gender. So I will call it a cell, so the select, I will select age and genders out of the names of my DT file. And then I will create another data frame called covar, and then I will use DT, and then I want all the rows, and then cell. And then if I open it, I have the gender and age here. And something that is very important that we have to set up the structure, the class of the data. Now, so if you look at here, str covar, we see that both gender and age are written by R yet as a character. So this can lead to issues when we fit the model. So it's better that we provide the right class to the data. No? So in the case of age, the class is an integer. So I will use the function. So then we do this covar age as integer, covar age, and then it returns to me the warning. Remember about the warning. So this means that I got the result that I asked, but there is something that was happening that I should take care about. So what these warnings means is that some of the data that was inputted here wasn't actually an integer. So when R tried to read it as an integer, for some reason it did not identify it as an integer, and then instead of doing something else, R just turned the data into NA, a non-available data. So this is what they do. NA is introduced by coercion. So when it looks for the data and it cannot coerce into an integer, it just turns it into a not NA. So covar gender, and then as integer. Now as factor, I want it to be a factor. Covar gender. So then there is no thing here, but if I do summary covar gender, I know that I'm working with 463 men and 552 women. And then since we got this warning about the NAs, something that is important, that all the data, like the rankings and the covariates, are complete. No, so we cannot have any non-available data in the covariates. Should be complete. So then we have to look for the NAs, and then we have to take out the rows, no, the observations with the non-available data. So to do it, there's many ways to do, but I prefer to do in the more base R approach. So then first thing we do like first to check if there is any sum. So we call this function sum isna, and then covar, so it will apply to the entire data frame. So then I know that I have 8 non-available entries in the data set. So then I will create the same vector called keep, but in this case I will use the function called apply. So what this function do is that it will look for the non-available data in each of the rows of the covar data frame. So it will go looking for each of the rows in a systematic way. So to do it, I will call it keep and then apply. and then I want it to be applied to the covar, and then it asks which margin. So the margin here means that if you want to work in the data through the columns or through the rows. So in this case, I want to work through the rows, so then the margin is 1. If I want to work through the columns, the margin will be 2. So margin 1, and then I will call function x. So each row will be x, a function of x in this apply, and then I want to just sum is na x. So then if I look at keep, this will be a vector with numbers, no zeros, and the numbers should be between 0 and 2 because I have 2 columns. So the maximum of non-available data will be 2, and the minimum is 0 because that's what we want. No, we want the values equal to 0. So in this case, we take it the vector keep, and then we do another validation to the data. We do like this, a keep. So I want everything that is in keep that is equal to 0. So then this will return to me 1007 data points. So then I will just need to filter it. No, first thing I will apply the filter to both, to covar. So then will be covar keep, and I want all the rows, and then dt keep. And then if I look at the structure, is age and everything. And then for the Plackett-Luce rankings, we use the same ranking, the Plackett-Luce tree. We use the same rankings, but in this case, it's something called grouped rankings, because the grouped rankings will help us to link the rankings with the covariates that we already defined here. So here I use the same function rank tricot, but in this case I use the argument group true. That's the only difference between this one and this one here. That's the only difference. I just add the argument group true. So then I will call it a G capital, and then I have the G, the grouped rankings here, okay? And then I can use the function cbind to combine the rankings G with the data from the covariates. I will call it PLDT, so Plackett-Luce data, and then I will cbind G with the covariates. And if they have the same dimension, remember that that's why I applied this filter to both data sets. So if they have the same dimension, they will be fine. The bind will be fine. And then here we have the data. Now we have the one vector called G, the other one age, and the other one gender. And this is the structure now of the Plackett-Luce trees. And you see that the trees now, the Plackett-Luce rankings, there's a lot of things inside, and then the structure of the age and gender. And to fit a Plackett-Luce model with covariates, we use the function PL3. So this function PL3 runs the Plackett-Luce model behind it, together with the recursive partitioning tree approach. So I will call it PL. The object will be called PL. And then I will call the function PL3. And the first argument of this function is the formula. So the response variable will be the G, and the dependent variable will be the other that are separated by the sign, like this one, the by, what we call in R, it's called by. So then I will do G. So the name should be the same names. So let me look at here, names, PLDT. So the names should be the same that we find in the PLDT. So G by age plus gender. And then the data is PLDT, and that is it. But I did something different. Let me check here in the formula. In the lecture. Oh, yes, I used an alpha of 1, no? Instead of using an alpha, because the alpha, no, the alpha of the by default in the PL3, the alpha by default in the PL3 is 0.05, no, it's 5%. So in this case, since I'm working with the more like a socioeconomic data, I can have a higher alpha. So in this case, I will use an alpha of of 0.1. So if I run it, and if you want to look at what is happening behind, you can just yeah, this is I don't really remember. I think it's verbose true, something like this. Yes. So if I use verbose true, I can take the print of what is happening behind the panels, no, behind the covers in the when deciding when they are fitting the Plackett-Luce. So do you see a parameter instability test? So the first instability was for age, and then when it ran for the third time, then it says no, stop splitting, no stability anymore. And if I let me see what happens if I put a minimum size for the node min size of 30, for example. So then if I do this with 30, then it will split by gender. No, let me see, plot. Still splits by age, and then it shows that for example in the case of the Ghana data, no, this data. So when the participant is older than 49 years, the participant has a preference towards these three varieties here, which I still don't know because the plot is too small. And if the participant is younger than 49 degrees, 49 years, the participant has a preference to this variety and this one as well, and this one, these three varieties here, no, these three genotypes. So let's look at what are the genotypes here. I can do the summary. So summary and then reference ref. So let me see which one is the best. So in the case of the node 2, no, which is this one, node 2, when the participant is younger than 49 years, the varieties that the participant prefers are this one, Sariobari, and also this one, PG 17136, and also this one, Sarinan. And if the if the participant is older than 49, so then the varieties that the participant prefer are this one, PG 17, and then this one as well, PG 362, and also this one, Sarinan. But there is no significance between this and this. No, it's basically the same. It's the same significance level as the reference here. So in the package GoSet, we have a plotting method that helps us to visualize it a bit better. We call it plot3. But this function is not yet implemented like fully in the package, so I keep it like a hidden function. So to access this function, you have to use this command three dots now. So what we do is that we use a GoSet, we call for the package, and then we put a 1, 2, 3, 3 of these double dots, and then we call plot 3, and then I will just need to write PL, and then here I have the estimates, and then the varieties are in the y-axis, which is much better to visualize, and then we can see the error bars. So if I put it a bit bigger, so then I can see better. I can see it better. So then I know that when the participant is younger than 49, the variety that the participant prefers is this one, and this one. And when the participant is older than 49, the participant prefers this one and this one as well. And also this one. So this is what we see from this this plotting method, which helps us to visualize a bit better. So this was an example for you on using the Plackett-Luce trees for socioeconomic data. And now we are going to work with the breadwidth data from I have in CleanMob. So then we are going to use this to check how can we link Plackett-Luce trees, Plackett-Luce rankings with the environmental variables. For example, rain and temperature variables to see the effect of the climate on the performance of the crops. So to do it, I have this data set called breadwidth. This is more than 400 plots, farm plots in Vaishali, India. And this data set is in my account, the GoSet account. So then I have the key, the API key here, and then I will use the package the CleanMob tools to get this data into the R section. So then you can also see that's possible to connect with your data as well. So this is the key. You can also see the key in here, in the example tool of breadwidth. And then let's see. So then I will use the key, and then I will call for the package or for the data. I will call it a DT. So now I overwrite on the DT data that I already had before. So then this is the data that we have. We have the ID, we have the participant name, which is just a name that we just replaced here. We have the packages with the variety names. It's a breadwidth crop. And then we have the district is in Vaishali, and we have the gender, the age of the farmer, and also we have something that it's very important for this is the latitude and the longitude of the plots, which is important. And then we have also the planting date. So we know which date the farmer started the experiment in their farm. So and then the location, which is very important for this. So to take first thing that we use, let me see the names, the name of this. And then these names come with the data collection moments, like the strings for the data collection moments. So since I know that there's no duplicated in the names, what I'm going to do is just I would take away the name of the data collection moments. I will replace this with nothing. So I will replace these names here with nothing in DT. So now if I run DT, so now I have a more clean name, which is more doable to work. And remember that I also have to coerce the data to the right values. No? So in the case of the planting dates, I have to coerce it to date. So basically I do is just call the function as date. So planting date. So then I will call as dot date. And then I will use dt planting date. And the format of the date will be this one. Also, the first thing is the year. The second one is the month. And the third one will be the date, the day. So now if I do like a plot dt planting date, I know that the planting dates for this wheat trial ranged between November and December. And let me see, I can also use a hist. Let me see the density, for example. It says that should be a numeric. So let me see if I can plot in a box plot. Yes, so in the box plot also, we see that most of the dates were around December. So these were when the farmers started the planting of these wheat trials. And then I will also convert the longitude and latitude to numeric. I will call it in a new name called long, and the other one will be lat. So numeric. And then we are going to use the function called the temperature. And this function comes from the package climate-trends. So this function comes from the package climate-trends. And here is an explanation on how this works. Now, so this is the functions that we have available. So one is rainfall. The other one is temperature. The one that is called crop sensitive. The one that is called growing degree days. You can also estimate the growing degree days for your trial. Another one for reference evapotranspiration. And there are many ways that you can also read about the climate trends here, how it works and what we can do with this in the vignette of this package. But basically what the package climate trends do is that it takes the plant dates, the points that you input, and the dates that you input as well, and it will take the data from NASA Power, another package by one of our colleagues, Adam Sparks, and then it will take the data from NASA Power and will compute the temperature or rainfall indices for the time span that you provided. So, for example, if you look at the temperature, this will compute this kind of indices. We have the maximum day temperature, minimum day temperature, maximum night temperature, the diurnal temperature range, summer days, tropical nights, consecutive frosty days, maximum warm spell duration, maximum cold spell duration, and the 10th percentile of the night temperature, and the 9th percentile of the day temperature. So we are going to use, for this example, we are going to use only the climate trend, the temperature function from climate trends. And in this, there's many ways to compute it, but in this case, we are going to use function temperature. I will call it temp. and then temperature. And then the first argument in this function will be the geographic points. No? So then dt c, I want all the things. So long should be first the x and then lat. So this is the first argument. The other one is the day one. So from which day should I start computing the indices? So I will start computing the indices from the planting date. No? So then planting date. And until which day should I keep computing the indices? So the indices in our case here, I want to compute the indices from the planting date until 80 days after the planting day. So the first 80 days of the planting. So this will cover basically the vegetative period of the crop. No? In this case, the wheat. And then I use the argument called span. So the span will be 80 days after the day one. So if you have any questions here, just please take a careful look at the documentation in the climate trends, so then you can see all the examples that can be done with this data set. So then I will call it, and then it shows to me this message showing getting climate data from NASA Power. So it's done. So now I have all the indices here, all the indices that I was talking about, and then it's in this printing method. So then what I do is I pick the rankings of the bread wheat, and I will convert it into a grouped ranking. I will bind the data, now cbind the data. So if I do head that, I have the rankings and then all the covariates. And here I will fit a Plackett-Luce model using G by maximum night temperature and maximum day temperature. So I will fit the model like this. And if I do summary PL, I can see that there was it created two groups. One for when the day temperature is higher than when the day temperature is higher than 29 degrees Celsius. So then there is this performance here of the crops, and then when the day temperature is lower than 29 degrees Celsius, so this is how the crops will perform. So you see that basically what you see in difference here is that basically this one, CSW18, will have a higher probability of performing better when the temperature is lower during the days, in the first 18 days. So if I go to Gosset plot tree PL, then I can see the same thing. Showing this, now when the temperature is lower than 29, so then this variety here, CSW18, has a higher probability of performing better, so it can perform a second best. And when the temperature is lower, so then it goes to the third place, so it get weak when the temperature is higher than 29 degrees during the first 18 days, for example. The K9107 is the best variety in both cases, and this PW343 is the second best in all the cases. But the most thing that we see here is this difference for this third place. No? Well, it is the PW is the third best here and the second best here. So this is we see the difference between the changing in position, the second and the worst one, second and the third one. And we can also take out the coefficients here with the function coef, and then we just need to put it here. As I said before, if we just type coef, it will come only with the log worth. And if I do coef pl log false, it will come as the probability of winning. It's also possible to make predictions. Now, with the function predict, we can also fit the model and see the predictions based in other set of data. This is more to learning from the model. So, but I will only show to you like with the function predict. If we just type it here PL, and we get the probability of winning for each of the varieties in each row that in the data. And if we look at the type of the prediction, let's see which kind of a so predict the types of prediction that are allowed for Plackett-Luce is interparameters, rank, best, and the node. So if I do item par, for example, it will return to me the log worth. No, it will return to me this probability of winning. If I do the other one, let's see which one is the other rank. So it will return to me the rankings, which one will be the best one, the one, and then the last one. And also if I do node, it will return to me which node the variety will fall in. And the other one is best, which one is the best one. And I can also use this also called new data. And let's see that I want a new data over rows 1 and 1 to 10 of DT of that. So then it will return for me the predictions for rows 1 to 10 when the new data is when we use this argument new data. So if you want you can just also take a look on how the function predict works, because it works basically in the same way for all the model approaches in R. So you just need to look at how it works and you can learn more about it. And with this, we cover what we have planned to this course. I want to thank you for watching this, and yes, and then I look forward for the Q&A. So if you already finished this, I recommend you to digest, to think about what you learned here, and then you contact your team leader or your contact point to organize the Q&A section with me, so then we can work with your cleanup data, with your tricot data, and also solve further questions that you may have. Thank you.